Chapter 18 is on global climate change, which we also call global warming. The case study here is about the Maldives. So the Maldives is an island nation off the coast of India, and it's very, very low. That means it doesn't have a lot of mountains or high areas. It's very close to sea level. And this is a nation that might completely disappear if sea levels rise, which would mean that every person in that country would lose their citizenship in that country and would be a refugee that would have to move somewhere else. So these issues that happen around the globe with climate affect everybody else. All right, so first of all, let's talk about what causes climate change, what causes global warming. First, you need to understand what a greenhouse gas is. So we've had these gases around our atmosphere since Earth has been around, and they're actually really good because they make Earth's climate habitable, livable. Without these greenhouse gases, Earth would be too cold to live in. So they trap the heat and make the planet livable. The main greenhouse gas that we talk about a lot is CO2, but it's actually not the one that's the most. Water vapor is actually the most in the atmosphere. So you'll see that on a test question quite often, which greenhouse gas is the most in the atmosphere, which would be water vapor. However, if you see the question, which is the largest anthropogenically produced greenhouse gas, you would want to say CO2. So anthropogenically means human-made, and that would be CO2 because of burning fossil fuels. Water vapor is natural. We don't really influence it significantly. I mean, yes, we can build a dam and the evaporation will add to water vapor, but it's not a significant level to influence the vast amount that's already there. So anthropogenically made would be CO2. Some of the others would be methane from feedlots, from cattle. Their flatulence, their passing gas is methane, also from landfills, actually producing rice as well. And then nitrous oxide, CFCs and HFCs are also greenhouse gases. So some of these participate also in air pollution. So this is also air pollution. This one is also for the ozone hole. And so some of them function as double duty. So what do? Well, they warm the troposphere where we are because they absorb outgoing infrared radiation reflected back from Earth. So here's a picture up here showing you how radiation from the Earth comes down, and this is a different wavelength than what's reflected back from Earth. And so these gases here trap what's reflected back from Earth and send it back here to warm the planet. So without these gases, again, it would be too cold to live here. But the problem right now is that with our burning of greenhouse gases, and not just that, but our love of meat, produce more than we've had in the recent past, in the human past. And so that is contributing to a warming planet. So down here, carbon dioxide is actually not the worst gas for warming the atmosphere. These others are worse. They trap more heat. Methane does, nitrous oxide, but we don't produce as much of these as we do carbon dioxide, although methane's starting to get pretty close. All right, so let's talk about CO2 first. But this graph here shows that our concentrations of these greenhouse gases has increased tremendously since the Industrial Revolution. We have burned and burned more and more of these gases. So carbon dioxide is a natural produced gas through cellular respiration. So it's been around here forever, but it's always been at this equilibrium. So we as animals, as consumers, we breathe out CO2, and then plants take in CO2 and use it for photosynthesis. But the problem since the Industrial Revolution is that we now burn more CO2 and fossil fuels than what can be taken in by plants through photosynthesis. So we can say that CO2 is the most abundant anthropogenically made greenhouse gas from burning fossil fuels. So GHG is greenhouse gas. So some other activities that raise greenhouse gases, and I actually have these mixed up, so let me move them here. All right, so what do we do to raise greenhouse gases? Well, first we burn fossil fuels, which is CO2. We raise livestock, which is methane. We build landfills, which releases methane. So any kind of anaerobic decomposition will produce methane because the bacteria that doesn't use oxygen produces methane as a byproduct. So in fact, when we pass gas too, it's actually methane. But there's way more cattle than there are humans, and they're bigger than us. So really it's the cattle that are producing the vast amounts of methane from digestion in the intestinal system. We produce fertilizers for nitrogen, for our NOx. We deforest and we burn the trees. So burning the trees emits CO2. Just chopping them down and using them for lumber prevents CO2 from being sequestered by the trees. We grow rice. Now, rice is actually grown in flooded fields, and that water, along with, once you harvest the rice and you let the stalks decompose, they're going to decompose underwater with less oxygen and produce methane. And then new dams will produce methane too because they flood the area behind the dam, and so all of that flooding will flood huge amounts of vegetation that then decompose underwater, and so new dam construction will actually release methane behind the dam in the water that's trapped, that flooded forests or other plant material that is decomposing now under the water without oxygen. So it raises the BOD. Remember that term, the biological oxygen demand? And so the oxygen levels go down, which means that the decomposition is happening without oxygen, therefore releasing methane. Another type of climate change, so it's not just global warming in this chapter, but sometimes we have cooling effects. So sulfate aerosols can block sunlight and cool the atmosphere. We get these from fossil fuel burning and volcanoes. So burning fossil fuels also creates CO2, which warms the atmosphere, but it also temporarily can also emit sulfate aerosols. Volcanoes, all of the particles that they emit can also block heat. We saw this happen in the 1880s with a volcano in Indonesia called Krakatoa. And when it erupted, it emitted so much sulfate particles into the atmosphere that summer it was so cold that crops didn't grow in Europe, and they had famine because of that volcano all the way across the world. All right, so over here we have the Milankovitch cycles. The Milankovitch cycles are how we explain the natural fossil record of heating and cooling time. So how did we have previous ice ages? How did we have previous warm times with dinosaurs? And they are explained through the Milankovitch cycles. So we have a wobble on the tilt, we have a variation of tilt, and we have a change in the ellipse of the sun around, or the Earth around the sun. So some people will say that, oh, we're in a natural warming phase because of the Milankovitch cycles. So people that study that, I mean, that's a valid thing, and so we've studied to see if that is the case. And what we found is that actually we should be in a cooling phase right now from the Milankovitch cycles, and we're not, we're warming. So that is not a way to explain our current warming of the planet. In the oceans, the thermohaline circulation may be disrupted, and so this could lead to all kinds of new weather patterns because the oceans dramatically influence our weather. And so without this deep circulation, you may have the Gulf Stream disrupted. Now the Gulf Stream makes Northern Europe habitable. So Northern Europe might actually get colder because they don't have the Gulf Stream bringing warm water up to them. These are all things that may happen. We're not quite sure. You know, the Earth doesn't always behave the way we predict, but this is possibilities. All right, so how do we know the Earth is changing and warming, and it's due to human causes? So we as scientists have done a lot of research. 95% of scientists believe that climate change is being caused by humans because of the data. So scientists will look at peer-reviewed, published data to see what's going on with the climate research. And so we have these things called proxy indicators. And a proxy means that we weren't there. So there weren't humans 20,000 years ago measuring climate. So how do we know what the climate was like 20,000, 30,000, 100,000 years ago? So these are things that we do to study and find out. So we take these ice cores, so we go up to Greenland, we go to Antarctica, and there's a picture here of the ice cores. And what we do is we melt them, and then we analyze the gases that were trapped to show at what period in time certain gases were there. And so we can also tell the temperatures and pollen and things like that. So we put all this data together from ice cores, from sediment beds. So we date the sediment beds, and then we see what kinds of pollens and grains were preserved there. So if you have this sediment bed up in Canada with some tropical plant pollen that has been preserved from 20,000 years ago, well, then you know 20,000 years ago in Canada it was warm because there were tropical plants there at the time. So, and then we can also look at tree rings. So tree rings can go back as old as a tree. So 1,000 years maybe for the oldest trees, maybe 2 for like some of the cypresses. But the redwoods go back hundreds of years, and even 1,000 years or more. And we can see droughts. And so in California, we want to know, is our drought long-term or not? And so we can look at old ancient tree rings to see what has happened in the past. So pack rat middens, it's like their little cave that's been preserved. So we can find these ancient middens from these pack rats that left stuff and abandoned it or forgotten it, or they got eaten or something. And we can see what kinds of seeds that they stored 500 years ago, what was growing in this location. And then we can also study coral reefs because they take in isotopes that reveal what the water chemistry was like. So was it more acidic? Was it less acidic? What kinds of dissolved gases were there in the ocean? And so these are the things that climate scientists are doing. They're not just guessing. They're looking for evidence for or against human causing the warming on our planet. So, and we, again, these are the evidence for proxy indicators. All right, going on 2 pages to 492, we have the Mauna Loa graph. So the Mauna Loa graph is actually still, Mauna Loa Observatory is in Hawaii, on the island of Kauai. Actually, I'm sorry, it's not on the island of Kauai. It's on a little island that, actually, I don't know where it is, what island it is, but it's in Hawaii. And it is a map, a graph of carbon dioxide levels. So there was a scientist named Keeling who wanted to see if, and get data to show if carbon dioxide levels have been increasing or not since the Industrial Revolution, but we don't have that data. So in 1960, 1958, he said, okay, well, let's start measuring now. And so he found this place in Hawaii, and I'll tell you why on the next video.